classic vote.
The what?
I'm on that vote too.
Yeah. Yeah, but we actually ended ours and you have.
Hey!
You got on video!
Hey! I said we're on the same boat. I didn't say what part of the boat or how long the boat was.
He's the one hanging on, trying not to drown.
You want to like
I'm technically on it, I'm holding on to it, right?
You're on the poop deck.
Oh, no, yeah, floaty. He's on the poop deck.
He's with a floaty?
There's like like the stair post just hanging on.
It's
a lifeboat?
Yeah, but it's like hanging off the side.
Yeah.
Hold on.
Well, today, folks, we're going to explain where the plus minus comes from when you're solving a quadratic equation by taking the square root of both sides, because it just magically appears. And without a really proper understanding of why, what, I mean, and I know when I first started teaching, I answered it very poorly to students probably. You know, most students don't care, and they'll say, okay, yeah, I'll just remember to do that. But it doesn't make any sense, what I used to say. So. And then, it kind of goes along with that. Explain what the square root of x squared simplifies to. Most people would say, well, it's easy. Square root of x squared is x. If you think about it, isn't what we do if you were going to simplify, well, let's put x squared, y to the fourth, and then even z cubed. We'd probably all write down x, y squared, and then a z, and then square root of z. And you look at the back of the answer and get it right. It's exactly, I guarantee that's what the back of the book says. Problem with that, well, there's a problem, is that square root of x squared may not necessarily be just x. So we'll see what happens. Yeah, leave it at that right now. And then hopefully we're going to walk away being able to derive the quadratic formula, maybe in more than one way. And did you find that was pretty? Did you also check it with the quadratic formula? When I asked you to do that extra one, did you do it? You had to get that out of the notes though, so if you didn't, or out of the lesson plan. Oh, so maybe if I should put that in here though. Actually, let me write that down for next year in the notes, because that was kind of an add-on from last year. In the notes, that's number 14. Is that page 49? I actually gave you another quadratic formula that wasn't the quadratic formula. Oh, you did. And I said, I showed you that, but it's not in here, so if you only mark down in your notes, then you were supposed to do up to number 14. Write this down for next year. What was last Thursday? For what? 27? Yeah.
You're on fire.
Good. Okay, so let me review with two little questions that are the similar kinds of questions that I'm going to ask you next week on for our final exam time. I'm just going to go through these things, and probably the best place to kind of review some questions will be go pull up the lesson plans and say, okay, what kind of questions did he ask for review? Look at these questions here, because some of them are questions that students might ask and say, okay, how would I answer that? Can I answer that? So, what is the difference between an exponent and a power? If somebody says that, now there's a sense to that question where you could probably get away with saying, well, a lot of times they're used synonymously, and so there is no real difference. And that's true, in some sense of the word we've seen in the dictionary definitions. But is it possible to distinguish between the two? How would you answer that if somebody said, is there any real difference between exponent and a power? What would you say? How could you say that? So, given, how could you answer that? Given 3 to the 4th equals 81, not just about point to the exponent, point to the power. So I think after last week's, seems like a year ago, after last week's discussion, we would all say the exponent is what? 4. The power is what? 81, right? The power is 81. So in words, rather than having to look at this example and say, oh, the power is this and the exponent is that, how can you answer in a coherent sentence or two what the difference between exponent and power is? The exponent is the, so you finish my sentence hopefully. The exponent is the what?
Number of times the base is multiplied by itself.
Okay, and we're going to be careful with that. The number of times the base multiplied by itself, we decided that really probably is used as a factor, right? So the number of times used, or we could certainly even say that if we understand that to be the meaning of the exponent, we could even say, well, the exponent is the little superscript number, right? And then, okay, what's the little superscript number mean? Well, it means that how many times we're going to use the base as a factor in a multiplication problem. But again, if we say it is common to say it's the number of times you're going to multiply by itself, we do at least understand that, and I'm not going to be picky about that right now because I'm just after how do I distinguish that in words between the exponent and the power. And then how would I describe then the power? If the exponent is actually the number of times you're going to use the base as a factor, then the power is what?
The product of the equal factors.
And this may be a good way to remember P and P, right? The power is actually the product, right? The power is the actual product. And and we don't use that word. I wish we'd use the word more. We say when you multiply it, right? How about this? Negative times a negative is a positive, right? Well, and in fact, did I screw up on that? Let me see. Multiplying negative. Why does a negative times a negative equal a positive? That's a garbage. I'm circling that and changing that for next year.
Why is the product positive?
I want to use some good math terms, right? We say negative times a negative, and actually, my son's 5th grade class was doing something like that. What are they doing? They're multiplying two things. They're multiplying two things to something, and I reworded it for the teacher too. I said, I want you to think about it another way too. I want you to use some good math words, and I said the product of whatever it was. But yeah, I mean, why don't we use better words? Negative times a negative. That we say that because we read 4 times 3 equals 12, right? So if it happens to be two negative numbers, we say negative times negative equals positive. Why can't we just look at that thing? Why can't we distinguish between, how about these words, translating something and transliterating something? Transliterating is a word for word, or sometimes even a letter for letter translation, whereas a translation is taking the whole thing and translate. So if you're transliterating French into English, the French say, I'm going over to the house of John. Okay, that's a transliteration. But we would never look at that. If somebody was actually interpreting it, you say something, I say something kind of a thing, no one's going to say, oh, I'm going over to the house of John. They're going to listen to what the person said in French, and they're going to say, I'm going over to John's house. That's the difference. So here we say negative times, but why don't we say product of two numbers is a... Well, so I like what Ashley said. The power is actually the product, the answer, right? And then why does cross multiplying work when you're solving proportions? Why does cross multiplying work? We do it. We do it well. But what are you doing? It's a shortcut method, so I might say that. For what?
Systems of equations?
No, not proportion. I thought you said it.
Of getting a common.
Of getting a common denominator, right? Solving a proportion by cross multiplication is a shortcut method. It's not the way we do it. It's a shortcut method for getting a common denominator, and then get really the quick common denominator. Remember we said that, not the least common denominator, really quick common denominator. Yeah. Okay.
There could be some cases where it's the least.
And it could be, right, it could be.
I'm not going to defend that.
Well, and actually though, from a pedagogical standpoint, when I'm creating my lessons, and this is why I was talking to Block 1 students today, and even though I'm not, I'm not a creative person like going out and, painting, drawing, and building, anything like that. My art, I feel, is my teaching, so like when I sit down, I may know how I can just tell people to do stuff, but my art, like the creative side of me comes out and says, so how can I, start from here, start from what they know, and get them to understand, this new thing or whatever it is. So from that respect, that's why I don't want to just come in and wing it in classes, because if I just make up a proportion problem and I want to, if I want to make up a proportion, if I end up making up a proportion off the top of my head, what are the chances that it's going to progressively bring them along? When what I'm sitting down thinking about is the first example I give them, the quick common denominator is going to be the least common denominator, because that's the way. Because I don't want one of the kids to say, well, what if I just get the least common denominator? Or if I say, because I will probably say, get the least common denominator, because at that point they're going to be done with getting common denominators the quick way. They're going to say, well, I always get the least common denominator. So I'm going to say, get the least common denominator. Go ahead. Well, but if it's a 3 in the denominator and a 4 in the denominator, then of course least common denominator is going to be the 3 times 4. Well, then the next problem I give will not be, these wouldn't be relatively prime. These wouldn't be relatively prime, and then I would be able to say, well, get a common denominator, or at least get a common denominator by using the product of these two, and then I can, continue to progress my students' thinking along to just seeing why it actually works. But it's a shortcut method for that. Okay, let's roll. Number page 45. Oh yes. Okay, so week 45. Right? Page 45?
Yeah.
Page 45.
Oh.
So number 12.
I thought we were okay.
Now, number 12 says this, right? And we know how to do this. If we said to solve x squared equals 16, most of us would say something like this, and it would probably look like this on our papers. We would say, take the square root of both sides. And I always think it's a good idea not to do it right inside the problem, because then for students' notes, then you've messed up the original problem. So I always like to think about the original problem first. And then we'd say, okay, well, square root of x is x, and the square root of 16 is plus minus 4, something like that, okay? I do want you to see that there is a little bit of an issue here, because you're going to say, well, there's no confusion to me, but you're the teacher and you've thought about this, because if this is problem number 3 on a test, it's very likely that problem number 1 on the test is this, and you want the answer to be that, okay? And when the kid puts that, you might be looking at an answer key somebody else made up, or a question from the book, and you say, well, that's wrong. Why? Because the book says it. And then you got to come up with a good answer. Why this is that? Because if you're going to accept this, think about this. If you're going to accept that, and you mean that, then you also better accept that. You see the logic in that?
Just word your question as positive. What positive integer can you get?
Well, and that is going to be, well, I like what you're saying. Hang on to that thought for a second, okay? Because this is kind of a mixture between these two problems. So then probably a good wrong. Well, I'll say a good wrong. It would be an acceptable wrong, an acceptable incorrect response to a student that says, why do you put the plus minus there? Is to do what I often said when I first started teaching, is to say, well, whenever it's in an equation, whenever you're taking the square root of x squared in an equation, then, or the square root of 16 in an equation, then you put the plus minus. That's a pretty pissy answer, this poor answer. It doesn't make any sense at all. There's no real logic to it. Whenever you're there, you put the plus minus. It's true, and you'll see where it comes from, but it's a pretty inadequate answer to it, okay? The key, though, is this. It's kind of what Ryan said. He said, well, for this one right here, why don't you just say, I want the positive 1? And I'm going to say this. You did. You did. Because that's what this darn symbol means. That symbol right there means the principal square root, the main square root. Okay, the one that has the same, or well, can I say that? Well, for square root, it's positive. But the principal, yeah, the principal square root. So let's go back though and get some of the things I want you to take away from this.
I don't understand why we tell them they have to put the plus minus ones in the equation.
Yes, that's what we'll get to. And it's because of something that, again, if you don't read your stinking textbook and stay off of the internet so much when you're trying to plan lessons, because those are things people just put up there, and I'm not saying it's all bad, but sometimes they're lacking in their explanations, and then we walk away with a bunch of students and also teachers who don't really fully understand the content rather than, and just follow some procedures. All right, so the first thing I want you to take away from is this. The square root of x squared is not x. Now, you're gonna have to bank that for a second because I probably should have put number 13 first instead of second, okay? But you're just gonna have to take that for what it is right now, okay? Second thing I want you to take out of this is an explanation that states we put the plus minus in front when taking the square root in an equation is lacking. Okay? It's lacking. It's wanting. It's inadequate. Third thing, teachers should not follow the following steps without clear explanation. The following steps being x squared equals 16, square root of x squared, square root of 16, x equals plus minus 4. You should not do that without clear explanation, which is what I'm hopefully going to explain when you're done with that. And maybe I should at least do this. I'll put up 1 here, 2 there, 3 there for my steps. The main thing here to take out of this is the leap from step 2 to step 3 uses what is called, now I'm going to call it something new because you got to think about it. I mean, there's nothing else that you know in algebra that allows you to do this. What I mean is, certainly you can take the square root of both sides, all right? But if you just are going to say the square root of x squared is x, and the square root of 16 is plus minus 4, I'm going to tell you both of those things are wrong, okay? I just said up here, square root of x squared is not x, all right? We'll get to that in a second. And then the square root of 16, and I'll get to this too, I'll formally put this up here, but that symbol right there does not mean give me either the plus or minus. Now it is true this, If I ask you in words, or if I write this phrase down in English, what is the square root of 16? You can tell me 4. You can tell me -4. Because I asked it to you in words, okay? Because the concept of the square root in words, the concept of the square root just means give me something that you can square all by itself and get the number you just asked me, 4, -4. But that symbol is very, very special. It's not just it's just not so we don't have to write the square root in words. It means something special. It actually says, give me the principal square root. And so don't say the square root of 16 is plus minus 4. When the square root of 16 written like that is 4. Okay? When you do that, the step from I'm not saying that those steps aren't right. Those steps are right, as long as you know this. It uses what's called the square root principle. Now, I find it interesting that this principle is PLE, but when I say that's principal square root, it's PAL. Because principal meaning the primary, right? Your pal, the primary person in a building, the principal, all right? That's the primary one. This right here is a law or a rule, right? So it's kind of interesting. Compare them. So it's square root principle. Now, well, and I might even say this, and should be proved. Not only should be proved, it can be proved because it only takes 30 seconds to prove, and every stinking high school student ought to be able to get it. You're teaching this in Algebra 2, maybe even Algebra 1, but it's easy. It's one line. So, let me see. Yeah, okay. Furthermore, I'm going to say that is probably what most of us will do, but you don't even have to do that. I'm going to tell you this. The square root principle really just goes from step 1 to step 3. But anyway, I'll show you that in a second here. Not a solution, a process. A process of taking the square root of both sides is not really used in the solution method. Rather, it is used in the justification of the principle. The principle that I'm about to show you here. So it's kind of like a theorem here. So let me step back here and make sure we understand what I just said. A process of taking the square root of both sides, which is the step from 2 to 3, right? Taking both sides. The process of taking the square root of both sides, it's not really used in the solution method. So what I mean is, you don't really need step 2. You can go from 1 to 3 if you use the square root principle. But to prove the square root principle, we use step 2, but you're missing something in between. You're missing a 2.5. You're missing the proof. Okay, you understand what I'm saying? So here's the deal. What I mean is this. Technically, you need 1, 2, 2.5, 3. Okay? Now, we don't do that if we understand the proof of what I'm about to do. But if we understand the proof of what I'm about to do, you don't even need 2. You just go from 1 to 3. Because I'm going to tell you what the square root principle says. So, the square root principle, says this. Now you're going to look at that and you're going to say, well, somebody's made this crap up. If x squared, they made it up so you could use this, and so many teachers don't understand this, that's why they can't even talk about it, which is pretty much the easiest thing in the world to talk about. If x squared, this is all it says, if x squared equals a, then x equals plus minus square root of a. That's it. Now, the unaware teacher looks at this and says, yeah, of course, you just took the square root of both sides, right? But you have to be careful with that. It looks like you did, except for the fact that the square root of x squared isn't x, which I'm going to prove in a minute, and the square root of a isn't plus minus square root of a. Okay? It's just the plus square root of a. So we got a problem. Well, then how can I use that? Because what I'm going to say is this. If I really know the square root principle, right? Because isn't that what it says? It says if x squared equals 16, then there is no middle step, folks. It's not, take square root of both sides. If x squared equals 16, then x is plus minus, that comes from the property. And what's the square root of 16? 4. So that's what it is. Now, what we say is, what a lot of people say is, well, what do you square to get 16? And what do you square? We square plus and minus 4. And that's fine because you're looking for a solution, right? X squared. You're not asked for just what's the square root of 16. You're asked for the stuff that you can plug in to get 16. And the answers are plus minus 4. So if you want to argue that way, that's fine. So you don't need that middle step, and that middle step confuses students because, but everybody does it, but because you take the square root of both sides and you say square root of 16 is plus minus 4 until that student says, I thought you said that square root of 16 was the principal square root and it's just 4. And then you're stuck saying, yeah, but in an equation you put the plus minus because you don't know what else to say. Okay? The reason is because of this. Now the question is this. Because once we prove, you've learned this right throughout your math career so far. Once you prove something, you just use it. You don't need to keep proving it, right? So if this is a statement that I can use someplace, if I prove it, if I can justify it, then I don't need to do anything else, right? I mean, I just use it. Well, all right, so prove it. All you have to do is say this. Let x squared equals a. Okay? That's your start. Then, now I'm going to do something you said, well, I thought you couldn't do. But I'm going to say, let's go ahead and take square root of both sides. But you said you couldn't do it. No, I didn't say you couldn't. I said you don't do it that way over there. I'm going to use it to justify this theorem. Then the square root of x squared equals a. Now, here's the kicker. And if you got number 13 right, okay, what the square root of x squared is, you're going to see what I mean here. Thus, now I am not going to put x, because the square root of x squared is not x. The square root of x squared is absolute value of x. Okay? So the absolute value of x is the square root of a. Now, here's the key. Now you go back to what you know about absolute value. And that comes from common sense. There's no proof of this. But when you say this, if the absolute value of x is 4, because of the definition of absolute value being distance from 0, right, there's 0, the answers to this, there's no proof for it. The proof is, because of the definition of absolute value, the absolute value of x equals 4 means that x is 4 or negative 4. This is by definition. So, once I get down to here, right, I can just say, by definition of absolute value of x, absolute value of x is plus minus square root of a. Oops, not absolute value, sorry, x. X is plus minus square root of a. Now, I've just proved this, and now I just use the heck out of it. So what that means, hold on before you ask something there, what that means is, for the next problem, now, I know what a lot of teachers are going to do. They're going to do this. If it says solve x squared equals 36, then I invoke the square root principle, and I write, now, the ignorant teacher, when I say ignorant, I mean unaware. The ignorant teacher says, I need to see steps. And they mean they want you to see the square root. That would be just, well, I don't want to say it'd be wrong. You'd have to understand that they just invoked the square root principle, okay? Or this. Again, I'm not saying you have to do this middle step, but you have to at least understand what you're doing. When you do this, when you take the square root of 36, you can go, if your next step, if you want to put this down, that's fine, as long as you say you are now skipping a step that says, right? That's the step you're skipping, or the step you're skipping. That's the step you're skipping. From there, you can say that. Get it? But when you don't put that there, I'm not saying it's wrong if you understand it, it's okay. But the point is, that jump is leaving students with thinking that the square root of x squared is x, and the square root of 36 is plus or minus 6. And those are both two things that just are not true. So I guess maybe to summarize that, to say something like this. So when, and I'm just going to abbreviate, solving using this method, and you know that method is taking the square root of both sides. When solved by using the method, do one of two things. First, do this. And this would probably be the best thing, I guess. X squared of 16, the next line is x equals plus minus 4 by using the square root principle. And then I'm done. Or 2, x squared equals 16, square root of x squared equals square root of 16, absolute value x equals 4, doesn't equal plus minus 4, absolute value of x equals 4, and then x equals plus minus 4 by definition of absolute value. Either one of those two are better. Either one of those two. Either one is better. Either one is better. Not either one, all better. Either one is better than mixing them up and leaving students thinking square root of x squared is x and square root of 16 is plus minus 4. Were you going to say something else, Cody?
I was going to ask how we get that the square root of x squared is absolute value of x.
Ah, okay. So, because that's the next question.
Yeah.
So let's look at that. Let's look at number 4. Or 14, right? 13? Oh, 13, yes. Look at number 13. Number 13. All right, so square root of x squared equals what? That's the question. So let me show you this. I'm going to go back to what I said before and say the square root of x squared is not x. Now, if it isn't x, if it is x, I better be able to prove it. If it isn't x, I better have a counterexample, right? So, let x equal -2. Okay? Let x equal -2. Then, well, do it this way, I guess. Then x squared equals 4. Agree? Because remember, the square root is a grouping symbol, just like absolute value, just like parentheses, just like brackets, which means do what's under there first.
Yep.
So x squared is 4. Square root of 4 is 2, right? And 2, do you agree, is not the x you started with. You started with x is -2, right? So clearly, this is not true. Second thing I'll say about it is something you've never done before. Because why would you? Because the square root of x squared is x. Right, okay? I'm going to do this. Let's graph that. Now certainly you can make a table, but in the interest of time, I'm going to make a table very quickly. I'm going to say, let's graph square root of x squared. You've never punched this into your calculator before because why would you? Square root of x squared is x. I need an x. It's not even plus or minus x, because plus or minus x would be this, right? And that whole line, right? This is the whole line is y equals x. The whole line here is what? Does that look like anything? Absolute value, right? It's the absolute value. Son of a gun. No, I mean, right? Why? Why is it absolute value? Well, let me see. What's my table, right? So we're going to make a quick table. Of course, when I plug in 6, I get 6. But when I plug in -3, well, it knows its order of operations. It does the squaring first, and then takes the square root. It's 3. So certainly, so it's the same function as absolute value, right? So I can certainly say that then that x squared is actually the absolute value of x. The third thing, though, I do want to be careful of is this: is again from the graph, y equals x squared. Do not say is plus or minus x. Okay, look at the graph. Again, if it was, you understand if it was plus minus x, it would be that line like that and that line like that. Okay? So it's definitely not that. Now, again, read your flippin' textbook. If there were 2 more weeks in the semester, the flippin' would probably change to another word. So my fourth thing is read, what did you say?
Yeah, darn.
Darn it. Textbooks say the following. And again, there are very few times that I'm going to say, and I'm not saying that textbooks are always right, but I'm going to say there are very few times that they actually, say something that is really just incorrect. I mean, they go through editors, usually it's a mathematician and math people, but at the same time, they're this thick, right? So there are bound to be some mistakes, and some people dwell on the 5 mistakes out of 687 pages, and it's like, this is a terrible textbook. I'm like, really? Because if I wrote 687 pages, it'd be a heck of a lot more than 5 errors, right? But anyway, this is not a place. Remember we talked about the definition of average, right? And we said textbooks, they're not wrong, but it doesn't give a complete picture of the definition of average, okay? So textbooks say the following. The first thing they say is this: a square root. So when they're defining square root, they say a square root of a number b is a solution of the equation x squared equals b. This is just a good way of, I know there are different ways, and this is why you read different textbooks. There are certainly different ways to think about various math terms. You know, it's called different representations, right? You know, we always want to, we don't share all of our representations to students, but we should understand various ones ourselves as teachers. Certainly you could say, well, I thought the definition of square root was the number that you multiply by itself to get the number in question. That's certainly one way of thinking about it. It's an arithmetical way, okay? It's a 5th grade way, before I know the square root symbol and functions and stuff like that. But another way of looking at it is, you know, think about it. Do you understand this definition? A square root of a number b is a solution to the equation x squared equals b. Is that right? Yeah. What's the square root of b? Well, it's a solution to x squared equals b. Because whatever that square root, you take the square root of that and you square it, you're going to get the b. All right. Makes sense. And then it says this. This is a great continuing on definition. Oh, every. Got excited with my E words in math. Every positive number has 2 square roots. Now, from this definition, we can then say you can't take square root of a negative number. Right? Look at the definition. Every positive number has 2. Well, that's not actually true from just this definition alone, because there's nothing in there about reals. Because it just says every positive number has 2 square roots. It doesn't actually say what negative numbers have. I guess maybe you can imply that it doesn't, but that's a little bit extra there. But anyway, so every positive number has 2 square roots. Now, what does that tell me? This is why I say, if somebody comes up to you on the streets of Lock Haven, because they sometimes will, and ask you, hey Jess, what's the square root of 16? You say 4, or negative 4. Because what? Because every positive number has 2 square roots. That's the first thing. The second thing, though, that it says, so I guess maybe I should say, maybe you want an example. Example, the square roots of 16 are plus or minus 4. Okay, something like that. The second thing textbooks say is this, and this is the kicker. The positive, right, because they have 2 of them. Well, I want to distinguish between the 2, the positive and the negative. Because the positive one is more important to me. Really? Why? No, probably because of that stupid Pythagorean theorem. You know, I don't know, but probably because of geometry, which needs my numbers to be positive, right? Because I can't have negative distance. But certainly, you know, when the square root appears and you want to put in a number that is a geometrical kind of a number, or not to say geometrical kind of number, a number that describes some geometrical property like distance or length or something like that, then the positive one is the more important one. So we distinguish like this. The positive square root, because remember, every positive number has 2 square roots. The positive square root denoted, now watch how it's denoted. Notated by, we're going to invoke a special notation for the positive square root. You all know it and love it. Okay? Denoted by square root of b is called the main, or the principal square root. Even I looked at an older textbook, my 1901 one, and it says the symbol nth root of b is read, we would read it now as the nth root of b. It actually said it's read the principal nth root of b. Now, I haven't looked into the history of this. My thinking probably is, my logic tells me is that that was probably early on. Like, I don't know when that symbol was used. What is it? Yeah, history did tell us. The history of math book that we have actually does have the history of that, when that was. I don't know if that was like in the 1600s or what, but at least when textbooks were being written, you know, a lot now, 1900, whatever, late 1800s, then they probably they didn't get lazy, right? You know, they just said what it actually was. So they would say the principal nth root of b. Okay, now, and then the last thing about this, though, is probably the most important, because go back to that problem that I said when working in problem number 12. Remember that I said nobody in here or any teacher out there is going to disagree when you do this and you say that. That's fine. What have you done when you said that? You've said that the square root of x squared is x and the square root of y squared is y. But you didn't read your textbook. Okay? We're not going to say that. You didn't read your textbook, because if you read your textbooks carefully, I'll say this about this problem. Textbooks feed into, I'm not saying they're wrong because they're right, they feed into this misunderstanding. They feed into, and what's the misunderstanding? The misunderstanding is that square root of x squared is x. Okay, that's the misunderstanding I'm talking about. They feed into it by stating, and when I say by stating, I will say this. Really, it's out of necessity. So out of necessity, really. I mean, otherwise, I want you to think about it. X squared, y squared, z cubed. What would your answer look like? Right? You see what I mean? You have a whole bunch of absolute values in there if you're going to do that, and that's not, you know, that's not going to be good. So here's what they say. Again, read your textbook carefully, and they'll say this: by stating that. Now, after a while, like I have a couple of textbooks in my office that actually do that. They take this square root of x and they start putting down absolute value bars.
That's what the one I saw did.
And then it's like, okay, am I really going to do this all day long? Read the next paragraph. Or read the beginning paragraph of the next sentence, or of the next section. Because it will say this. It will say, we will now, I think I copied this right now. We will now assume, because we can assume anything, and that's what you do all through your upper levels, right? You know, you have these axioms, we're going to assume this. We will now assume that now catch this out, no variable represents negative quantities. And remember my first counterexample. My first counterexample was let x equal -2, right? And then the square root of x squared doesn't equal x. As long as your variables don't represent any negative numbers, then it's okay to say square root of x squared equals x. Oh, but inside of an equation, go back to the last problem, right? Inside of an equation, square root of x squared sometimes does equal plus or minus. So which one's right? A proper understanding of the square root is the answer to it. So, oh, that was fun. That's it. So you looked in a book, and then saw it.
Algebra. Well, I saw.
Yeah.
I saw the principal square root is the absolute value of the number squared.
Wait, principal square root.
Yeah, principal square root. Like I looked where the square root section was, and it showed me the square root of x squared, and it had a rule saying that the principal square root is the absolute value of the number squared. Oh wait, no.
Well,
I added that in, I think, because
of the number.
Yeah.
Yeah. So the principal square root
is the absolute value.
The principal square root is the well, okay. So basically, no, that's right though. You either say it that way, but then you're building something in that's not really there, or you can say this, and that is the absolute value.
So then you have absolute value of the square root of x.
Yeah, right. You'd say that though. So hold on, something. Read that again. There's no example there. You said the principal square root.
I took a picture of it on my phone.
The principal square root is the absolute value, which I buy that. I'm just trying to figure out how to actually write that in algebraic notation.
Okay, so it says, notice that the square root of 7 squared
Oh, okay. Yeah.
and the square root of negative 7 squared both equal the square root of 49, which equals 7.
Okay.
In both cases, the principal square root is the absolute value of the number squared inside the radical.
Yeah, the number that is squared.
Okay,
Yeah.
Yeah.
Oh, I wrote it off this side on here. That's what it was.
I gotcha. Yeah.
Yeah.
So that makes sense, right? So
Yeah.
the absolute value is 7, and the absolute value of negative 7 is 7.
And it says that the property is true for the square root of any square.
Right.
And it
So
shows-
square root of any square. That's it. So now.
And it says,
There it is.
Yeah, for any real number, a
Yep.
square root of a squared equals a squared.
Now, you certainly know more about square root than you'll ever teach. But that still doesn't mean this, though. You know, I guess I tire, and you have to do whatever your cooperating teacher says. You know, when you're under their tutelage. But I would hope that if your teacher says this, if you start going off on this crap, you don't have to go off. You know, what I mean is, you know, if I was doing this right here, and they wanted you to take square root of both sides, I would do this, and I'd probably end up saying this. I'd say, well, that's the absolute value of x, and that is 4, and then say x equals plus minus 4. Okay. I guess you could, if your textbook does talk about the square root property or square root principle, you know, certainly this is the habit I get into. In fact, I've seen very few textbooks, and I've looked at a lot of them and seen that some do make a mistake. They'll say, take square root of both sides, and then something else. But a lot of them do say this. They just do that, and then off to the side in red, use the square root principle. Okay? That's what I'm in the habit of more doing. It's very possible that your cooperating teacher will say, I want you to show that, and then just write that. And don't try to explain it. My students won't, this is what I tire of. My students won't understand that. So every student in the world is an idiot, and they can't understand it. Or the people in that neighboring school district, they can understand it, but my students can't. Like, really? They live 20 miles apart. And they're that much
I'm
stupider.
gonna go off on my cooperating.
Yeah, no, don't do that. I don't
You're
think
an
it's that.
idiot. They don't understand.
They are, you know, they live 20 miles. That's why, you know, sometimes argue in university. It's like, you know, what's the difference? College students can learn differently than high school students. What's the difference between a high school senior and a college freshman? 3 months. Right? 3 months. All of a sudden now, they learn differently.
In all fairness, I was not an emotional wreck as a college freshman.
Like you are now? Is that what you mean?
I mean, as a high school senior.
Yeah.
I
Oh,
was
gotcha.
in college, yeah.
Hey, so seriously though, you know, know the common formulas that you use. You know, formulas, procedures, you know, whatever. You know, hopefully, well, we'll be able to derive them, the quadratic formula, but just thinking about that right there. You know how things like that are, you know, are obtained. So we're going to work on the quadratic formula probably all day Thursday. The last question, you should already know how to do, but take a look at it since that's the only thing you have to do for Thursday. It's just, what's a to the 0? Now, I want you to think about it. You know it's 1, I mean, as long as a is not 0, right? You know, we can't say that was 0 to the 0. But I want you to think about the same pattern you used for, and I wrote it right here. The product of two numbers, right? I actually remember writing, I was starting to type negative times a negative, and I was like, let me use some better math. The product of negatives. Remember the pattern we did? Try the same pattern with exponents. 3 to the 4th, then do 3 to the 3rd, then do 3 to the 2nd, then do 3 to the 1st, then do 3 to the 0, and see what the pattern shows you. Boom. Because most people will answer that question with, anything to the 0 is 1, and that's just a definition. Yeah. Hold on, it's not a definition. It's not a definition at all. I'll tell you what is a definition. 0 factorial equals 1, using that in probability, right?
It's because of
that has to be 0 because of the formulas.
It's because of the way they define multiplication as addition to, addition to 0. Or, yeah.
Wait, you talking about A to the 0 here?
Yeah, like.
Well, you work on that. There's a couple different ways. This is the easiest way. A pattern is the easiest way because you can't say you can't say this. 3 to the second is 3 as a factor 2 times. Well, 3 to the 0 is 3 as a factor 0 times.
But then you have nothing.
You have nothing. Yeah, exactly. All right, see you later.
Bye.
No, but I was thinking, because the one definition of multiplication I found when we were working on one of the other problems was adding the product of the 2 numbers to 0.
Wait, so adding the 2 products of the numbers?
Or adding the product of the numbers to 0.
Oh,
So,
adding the product numbers to 0. Okay, gotcha. So